Today I'm going to present the problem 6, planetary clock. First, let's look at the problem statement. Propose the most accurate clock that measures time with a temporal resolution of a minute or less using the rotation of the Earth. And the clock should work on another planet. So I highlight some important points that I here in the yellow font. So let's rephrase the problem statement and find out some key points that we want to pay attention to. First, we want the clock to be accurate. By that, I mean it needs to be stable, and we need a high resolution, which is 1 minute. And the mechanism needs to be closely related to the rotation of the Earth or the planet that is working on. We have an additional key feature that we want to pay attention to, which is the reliability. So we want to read the time at any moment in the best case, and we want it to work on different latitudes on that planet. Before that, we want to think about, we have some Q&As for this problem because we don't have a specific phenomenon to observe for this problem, so we take a different approach. Why do we need a quantity as time? Fundamentally, physics. As you may know, that whenever we are observing, whenever we are measuring a time, we need to know some quantity that we can directly measure. So we come to this important observation that actually, whenever we are measuring a time, we are looking for some relationship between one set of events and the other set of events. For example, if we have an atomic clock, we can relating the oscillation of the atoms and some other events that we want to measure. So here's our key formula for the whole problem, which is that the time interval is equal to the change of some quantity and the rate of change of that quantity. So what quantity is there to use in Earth rotation? First of all, we want to rule out some possibilities, and we will later focus on our proposal. First, we can use a clock that uses definition of time by solar day, which means that 24 hours is equal to a whole period of the rotation of Earth with respect to the sun. But this kind of clock has some disadvantages. Here I listed it in detail. And the second kind of clock is a clock that uses the principle of Foucault pendulum. But this kind of clock cannot work on the equator and will get increasingly more slowly as it is placed closer to the equator. Also, we cannot achieve a very high resolution with this kind of a clock. The third one is using the pure astronomical observation. But for this kind of clock, we still need to know the period of the planet beforehand. So that's some additional information, and we want to measure the time with as little information as possible. So here's our approach. We measure the angular displacement and the angular velocity of the Earth, and we calculate the time. This is quite fundamental to our approach. Here comes the theoretical part. So it is broken down into 5 parts. First, we derive the Segnet effect. It is basically an effect that uses special relativity. We have a loop, and we have some light traveling along the loop. And these are the derivation. I'll just test them really fast, and we can go back to them in the discussion part. So we come to a important conclusion. This is the formula for the angular velocity that is measured by the secant effect. Delta phi is the phase shift that we measure, and A is the area that is enclosed by the loop that we also measure in advance. And frequency is also a non-variable, which is the frequency of the laser, the light. And yeah. So how do we use this secant effect with the device? We propose that we can realize it with the optic fiber gyroscope, and it's a quite mature equipment that we can use, but unfortunately it's quite expensive. So we use data from many other experiments that people have done to support our claim. The other important principle is the conservation of angular momentum, because we want to measure the change of angle. So if we have angular momentum and it has zero torque, the angular momentum will not change through the time. But the planet is rotating, so there will be a relative change of angle between the fixed angular momentum and some base on the planet. Here's some, this principle is deeply rooted in the geometry of Minkowski spacetime of special relativity, but it is some kind of modified by the general relativity. But with the observation made by Schwarzschild, we can conclude that the Minkowski space-time structure is still applicable in our case. Here's some physics of the gyroscope, because it is not possible to have zero friction. So we need to consider how much the friction will influence our influence the accuracy of our gyroscope. It turns out that the error of the measurement of time that is due to the gyroscope is described by this formula. And from that, we know we want as small torque as possible. And at the same time, we want to increase the moment of inertia of the gyroscope and the rotating rate of the gyroscope. So this principle is realized with the electrostatic suspended gyroscope. So here's some possible method to calibrate the clock. We can also go back to this part in the discussion. Does this work? Does this work on other planets? Considering the angular velocity measurement, the gamma factor for other planets are also close to 1. So the secant effect, the formula that we derived for it is still working. The angular displacement measurement, the principle should work, but we need a high resolution. It depends on the resolution of the angular displacement that we want, and which means that it depends on the ability of our inertial gyroscope, and we'll come to that later. First, we take the data from the experiment done by Y. Pechurev's team. And what they basically do is measure the angular velocity by the gyroscope and take time as a non-variable, and they measure the angular displacement, and they got a very small error. We can reverse engineer the result to get the error in the measurement of angular velocity. It turns out that this error is quite small. It's 2 multiplied by 10 to the negative 6. And now we come to the era of the electrostatic gyroscope. And here's the data that we get from their experiment. As you can see, it's also quite small. By calculation, we can find it the time resolution to be 2.4 10 to the negative 15 second on Earth, of course. And here's the illustration of the gyroscope. So we use these two errors to calculate the time measurement error. And using the propagation of error formula, we have derived the formula for our error of time measurement, which is given by this formula. So we plot the function, and we found that it is more related to the error of the angular velocity. So by calculation, the error in 1 year is no bigger than 80 seconds, which is quite small. Here's some further insights. Have we achieved our goal? Yes, the clock is stable and it has high resolution. It works on other planets because the principle.
Sorry, USA, your time is up.
Okay. I can stop now. Yeah, this is the end. Thank you.
So if the opponent would like to ask any clarifying questions, I think my internet's caught up.
Okay, so first I would like to thank the opponent for a very nice presentation. It was a bit fast for me though. So I'm glad we had this debate now so that we can clarify some questions. First, I would like to overview what the opponent did. I think that the opponent thought the reporter did. I think he touched very well on all the relevant points of this problem statement. He didn't leave anything out, but there were some drawbacks to this method that was proposed. So first, what I liked is that the reporter specified time as the interval between events. So we really had this nice philosophical introduction to lead us into the technicalities. And then I also like the general formula for the derivative and the time interval. I think that was a nice addition. And then the reporter went on to propose time as the angular displacement over angular velocity. Now here, the reporter also criticized the Foucault pendulum and other such conventional methods and outright said that they can't be used, that they're not precise enough. I think that's to be debated about because they could be made well enough to work, I think, with proper calibration. So I think we have to have some numerical estimates before we, or at least better arguments before we throw them away. Then he went on to the Sagnac effect. Don't worry about this, Claudia, it was my misinterpretation. So the Sagnac effect was a special relativity effect proposed to measure time with an optical fiber gyroscope. The optical fiber gyroscope is, I think, a good idea because gyroscopes today are generally can already be made very well, both the electronic ones, such as this one, and mechanical ones. I was a bit disappointed that this gyroscope was chosen over Gravity Probe B, because Gravity Probe B's gyroscope has a lower yearly drift than this one. So I would like to debate about why this was so, because that one was the better solution. The reporter then went on to the calibration on other planets, which was done well, although because it was shown that it can work on other planets, but I saw no reason why Foucault couldn't work there and this gyroscope could work there. So I would like some clarification on that. Also, only planets from our solar system were considered, and we should also think about other solar systems which have stronger suns, other sonic winds, no atmosphere. There's a lot of wild effects on many planets, so we should consider all of them if we are to answer the problem statement. Then the reporter presented a very good experimental verification. It was a good review, and the experiment showed that it is a very good gyroscope, but maybe it's not good enough because its resolution was less than a minute per day, but its yearly drift was more than a minute. So if we are to keep time better than a minute, we have to do so after 1 year as well. And I was a bit disappointed by that. So I think we should, in the discussion, we should find ways to improve the resolution after 1 year, because that's the weakest point, I think. I think we have to talk firstly about calibration, because that was maybe what was lacking. Then on the key points of the problem statement, for the most accurate, I think the gyroscope is a very good idea. And the drift estimate was given. For the minute resolution, you did give an estimate, and it was good, but you should also talk about it on other planets. And after 1 year, I already mentioned it's not good enough. We should also keep in mind whether we're measuring relative time or absolute time. It may have been my misinterpretation. I didn't have enough time for clarification questions, but I would like some method of getting from relative time, which is what you're measuring, into absolute time. But you could probably measure the wavelengths. It's sort of a light clock on its own. So the discussion points, which I would now like to focus on, are presented here. They're mostly theory, but it's a theoretical problem. So I will be glad to enter the discussion now.
Yep.
So maybe first about Foucault. You said outright that Foucault can't work on other planets very well. Why is that?
If you have noticed the form that I attached in my presentation, there's the periods for different planets, and for some planets such as the Venus, the period is very large compared to that of the Earth. And for Earth, if you calculate it, and if you're going to use a focal pendulum, you will find out that you will need a pendulum that is that has a displacement, on average, displacement of like hundreds or thousands of meters to operate, and that is simply not so practical compared to our method. And also,
why exactly would it need to be so high?
Because you need a very small angular displacement resolution to measure a very small time resolution of less than a minute.
The resolution of 1,440 divisions of the circle, which
yes,
it's not so much. If you have a 2 meter wide circle, it's
that's just one part of the problem. The other part is that if your pendulum is operating on the equator of that planet, it simply doesn't work. And as it goes closer to the equator, the period also becomes larger. And
I agree with that. It wasn't part of the problem statement though, so that's why I thought that it was maybe a drawback that wasn't so significant for this particular problem. But I agree, Foucault pendulum is probably worse than this. So for the extreme weather conditions,
yes,
how well do you think your gyroscope would cope? So let's go to some other solar systems. You don't have any atmosphere. Wind is blowing at 200 miles an hour. There's ionic wind. Your magnetic field is dancing around. Some planets have a magnetic.
Yes. So thank you for asking that. So our clock actually is not influenced by the weather condition at all, because it could be attached to a fixed point on that planet, and the wind and other like factors just don't affect our clock.
No, I mean more ionic wind and magnetic fields, which are stronger on some other planets.
For that, you can just like use a metal box to shield the influence of outside, like electric field and magnetic field.
Okay.
Yeah.
Thanks. I was missing that because it was only the planets from the solar system.
Yeah.
So, one other thing, I think your gyroscope was very precise. I was quite impressed, but why wouldn't you calibrate it every once in a while? Because you have certain methods of calibration that also use only the rotation of the Earth or some other planets. So you could maybe have some slower clock to calibrate your clock more often, because the drift after 1 year was more than a minute, and that's not satisfactory.
Why is that not satisfactory? Actually, also the 80 seconds that I give is the upper limit. So it is in a range of the error, and the error that I plot is not exactly the error that we get from the experiment. So it's actually smaller than 80 seconds.
Okay, cool. Yeah, I'm glad you're clarifying this. So, but still, after let's say 40 seconds, but after 2 years it will be 80 seconds, and after 3 years there will be more.
Yes, and I guess that's true for any kind of design of clock.
Yes,
There's
but what if you had some sort of yearly calibration or daily calibration?
So
You use the rotation of the planet a bit better for calibration, I think, because your clock is great. Let's just try to make it greater.
So for any kind of calibration, we need another form of regular like oscillation or set of events to calibrate against. And for that part, actually, we need to build another clock, or we find some regularities in the motion of the rotation of the planet. But that doesn't necessarily mean that it's more accurate than our clock. It's just a bookkeeping of the time. So, for example, if you just calibrate an atomic clock against the rotation of the Earth, say you define the period of the rotation of Earth to be 1 day, which is 24 hours, and 24 multiplied 3,600 seconds, and you define seconds by that, and you calibrate it against the atomic clock. You count how many numbers of oscillations of the atoms are the number of the oscillations during a day, and you get a formula which is the total time that you measure divided by the number of oscillation of that atom, and you get a new clock. But that really isn't the goal that we want to achieve here. We want to achieve a measurement of time fundamentally independent of the working mechanism of another clock.
Okay, so you said that, so your clock is sort of measuring relative time. So the period of the clock on the Earth would be what?
Yeah, so here's another point I want to point out, like as an answer for your question. So our clock is actually measuring time using the special structure of the Minkowski spacetime given by the special relativity. So it is a fundamental, the rotation of the Earth, of the planet is fundamentally different than inertial frame.
Okay. But on Earth, what would be the period of your gyroscope?
There's no, the period doesn't really matter here, because we measure the absolute rotation of the frame of the Earth at any time point, and we measure the infinitesimal angular displacement at that time point. And actually, we can do an integral. So we measure the angular velocity and the infinitesimal angular displacement at that point.
Okay, so you have this clock that has a yearly drift of, we talked about it, 40 seconds. Why did you choose it over gravity probe, this mechanical gyroscope?
So it has the same working mechanism as a mechanical gyroscope. The only difference is that we use the electrostatic force to levitate the rotor, so that we have a minimum friction, minimum torque, so that it is more accurate with a smaller drift error. It is actually the same as a mechanical gyroscope, just smaller error.
Okay. We have one other question from one other team member.
Okay, can I ask whether how do you actually see what time is it on this clock?
Oh, yeah. So we have the formula for time, which is the angular displacement divided by the angular velocity. So what we are doing here is just measure the angular displacement. And by that, we can use this formula to calculate the time.
Okay. So you have a clock that can be used at any time of the day on any part of the planet.
But can you tell what time is it with a currency of with enough accuracy? Accuracy.
Yes. So I present this in the part of the experiment for the electrostatic gyroscope. The resolution of angular displacement measurement is 10 to the negative 17. And we use that to calculate the time resolution. And the result we get is about 2.4 10 to the negative 15 seconds.
Okay, thank you.
And that's quite small.
I think that the discussion was productive for both sides because it helped I think for us to clarify some of our questions because your presentation was very interesting. I think that it's a very good proposition, very accurate, but what would have to be worked on in the future is perhaps finding some sort of calibration, which I think could be possible only with the rotation of the Earth and only without any other standards. But I think that most of the problem statement was answered. And
do I understand correctly that you did not perform experiments yourself?
Right.
But you did cite somebody and use their results?
Yes.
So could you say what analysis did you do on top of their work? What was your contribution to the solution of this problem?
We have actually cited 2 experiments, and for each one, they get some error of the respective measurement. For the first one, they measured the error in the angular displacement, and in their experiment, time is taken as a non-variable. So actually, the error is solely due to the error in the measurement of angular velocity. So we reverse engineer the result to find the error in the angular velocity. And for the other experiment, the result is quite clear. They got the error in the measurement of angular displacement, and we just use that. And these are the things that we use from their experiment. So the further analysis we did is to actually calculate the error of time measurement that could be derived from these 2 errors. And we give
I understand your answer. I think we should let other jury members ask their questions.
Maybe just a comment related to the previous question again to the reporter. So as you didn't perform in person these measurements,
right?
So I understand the difficulties, all the difficulties of the problem, but how can you be sure about these very nice resolution you got? Can you really say I saw these numbers because I detected them?
I did not detect them personally.
Yes, you believed. I know you believed as a formula you have in a book, but okay, maybe this should be considered. Do you have any other idea how to perform this, to answer this problem? Maybe at the beginning.
You mean a different proposal of the mechanism of the clock?
Yeah.
Can I share my screen? So here we go. So these are some possible proposals that we excluded.
but you excluded because they were not okay. Apart the Foucault pendulum, you already discussed.
Yes.
Rest, because you were not able to perform because of any reasons we know, or just because you think it was not worthwhile to do this kind of experiences?
It's not as accurate as our proposal, just because the Foucault, and also it doesn't have as good reliability as our proposal, because the Foucault pendulum just as I said in this slide.
No, this we discussed. Yeah, sorry.
Yes.
This, no, yeah, we already
Yes.
discussed.
So
it's
that's
just
why
if
we
there was
explode.
a four hypothesis, a four proposal, or if you just stayed on these three.
Yeah.
Okay.
So these three are just three major types of proposal. Actually, we can come up with a lot of specific designs out of these three types.
Has the opponent other proposals?
Sorry, can you repeat that again?
No, the opponent, if the opponent has other proposals.
For what exactly?
To do the same measurements, not using what was proposed and what was already excluded.
So to make measurements with the reporter's clock.
Mm-hmm.
Well, first we would
to answer the problem with another kind of measurement.
We would first have to build a clock like that.
Yes, which kind of clock? Do you have another one to propose? This was my question. And then I stop myself, otherwise I will use all the...
Well, I think that if we were to make a measurement, it would be better to make some sort of mechanical clock, because this one would be much too complicated. I think that with a very good mechanical, maybe it would be realistic for a university to make measurements, or a very good Foucault pendulum, because the Foucault pendulum can be calibrated each sidereal midnight by observing stars. So all we would have to do is to ensure that the drift in one day is not too large, and then if we observe stars, we would have a very accurate clock, or we could just observe stars on their own if we had multiple observatories in the world, and we would have a very precise